In the year 1919, a virtually unknown German mathematician named Theodor Kaluza suggested a very bold and, in some ways, very bizarre idea. He proposed that our universe might actually have more than the three dimensions that we are all aware of. That is, in addition to left, right, back, forth, and up, down, Kaluza proposed that there might be additional dimensions of space that, for some reason, we don't yet see. Now, when someone makes a bold and bizarre idea, sometimes that's all it is. Bold, bizarre, but has nothing to do with the world around us. This particular idea, however, although we don't yet know whether it's right or wrong, and at the end I'll discuss experiments which in the next few years may tell us whether it's right or wrong, this idea has had a major impact on physics in the last century and continues to inform a lot of cutting-edge research. So I'd like to tell you something about the story of these extra dimensions. So where do we go? To begin, we need a bit of backstory. Go to 1907. This is a year when Einstein is basking in the glow of having discovered the special theory of relativity and decides to take on a new project to try to understand fully the grand pervasive force of gravity. And in that moment, there were many people around who thought that that project had already been resolved. Newton had given the world a theory of gravity in the late 1600s that works well, describes the motion of planets, the motion of the moon, and so forth, the motion of apocryphal apples falling from trees, hitting people in the head. All of that could be described using Newton's work, but Einstein realized that Newton had left something out of the story because even Newton had written that although he understood how to calculate the effect of gravity, he had been unable to figure out how it really works. How is it that the sun, 93 million miles away, somehow it affects the motion of the Earth? How does the sun reach out across empty, inert space and exert influence? And that is a task to which Einstein set himself, to figure out how gravity works. And let me show you what it is that he found. So Einstein found that the medium that transmits gravity is space itself. The idea goes like this. Imagine space as a substrate of all there is. Einstein said space is nice and flat if there's no matter present. But if there is matter in the environment, such as the sun, it causes the fabric of space to warp, to curve, and that communicates the force of gravity. Even the Earth warps space around it. Now look at the moon. The moon is kept in orbit, according to these ideas, because it rolls along a valley in the curved environment that the sun and the moon and the Earth can all create by virtue of their presence. If we go to a full-frame view of this, the Earth itself is kept in orbit because it rolls along a valley in the environment that's curved because of the sun's presence. That is this new idea about how gravity actually works. Now, this idea was tested in 1919 through astronomical observations. It really works. It describes the data. And this gained Einstein prominence around the world. And that is what got Kaluza thinking. He, like Einstein, was in search of what we call a unified theory. That's one theory that might be able to describe all of nature's forces from one set of ideas, one set of principles, one master equation, if you will. So Kaluza said to himself, Einstein has been able to describe gravity in terms of warps and curves in space, in fact, space and time, to be more precise. Maybe I can play the same game with the other known force, which was at that time known as the electromagnetic force. We know of others today, but at that time, that was the only other one people were thinking about. You know, the force responsible for electricity and magnetic attraction and so forth. So Kaluza says, maybe I can play the same game and describe electromagnetic force in terms of warps and curves. That raised a question. Warps and curves in what? Einstein had already used up space and time, warps and curves, to describe gravity. There didn't seem to be anything else to warp or curve. So Kaluza said, well, maybe there are more dimensions of space. He said, if I want to describe one more force, maybe I need one more dimension. So he imagined that the world had 4 dimensions of space, not 3. And imagine that electromagnetism was warps and curves in that 4th dimension. Now here's the thing, when he wrote down the equations describing warps and curves in a universe with 4 space dimensions, not 3, he found the old equations that Einstein had already derived in 3 dimensions, those were for gravity, but he found one more equation because of the one more dimension, and when he looked at that equation, it was none other than the equation that scientists had long known to describe the electromagnetic force. Amazing. It just popped out. He was so excited by this realization that he ran around his house screaming victory, that he had found the unified theory. Now clearly, Kaluza was a man who took theory very seriously. In fact, there's a story that when he wanted to learn how to swim, he read a book, a treatise on swimming, then dove into the ocean. This is a man who would risk his life on theory. Now, but for those of us who are a little bit more practically minded, 2 questions immediately arise from his observation. Number 1, if there are more dimensions of space, where are they? We don't seem to see them. And number 2, does this theory really work in detail when you try to apply it to the world around us? Now, the first question was answered in 1926 by a fellow named Oscar Klein. He suggested that dimensions might come in 2 varieties. There might be big, easy-to-see dimensions, but there might also be tiny, curled-up dimensions, curled up so small, even though they're all around us, that we don't see them. Let me show you that one visually. So imagine you're looking at something like a cable supporting a traffic light. It's in Manhattan, near Central Park. It's kind of irrelevant. But the cable looks one-dimensional from a distant viewpoint. But you and I all know that it does have some thickness. It's very hard to see it, though, from far away. But if we zoom in and take the perspective of, say, a little ant walking around, little ants are so small that they can access all of the dimensions. The long dimension, but also this clockwise, counterclockwise direction. And I hope you appreciate this. It took so long to get these ants to do this. But this illustrates the fact that dimensions can be of 2 sorts, big and small, and the idea is that maybe the big dimensions around us are the ones that we can easily see, but there might be additional dimensions curled up, sort of like the circular part of that cable, so small that they have so far remained invisible. Let me show you what that would look like. So if we take a look, say, at space itself, I can only show, of course, 2 dimensions on a screen. Some of you guys will fix that one day. But anything that's not flat in the screen as a new dimension goes smaller, 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 and way down in the microscopic depths of space itself. This is the idea. You could have additional curled up dimensions. Here is a little shape of a circle, so small that we don't see them. But if you were a little ultra microscopic ant walking around, you could walk in the big dimensions that we all know about. That's like the grid part. But you could also access the tiny curled up dimension that's so small that we can't see it with the naked eye or even with any of our most refined equipment, but deeply tucked into the fabric of space itself, the idea is there could be more dimensions, as we see there. Now, that's an explanation about how the universe could have more dimensions than the ones that we see, but what about the second question that I asked? Does the theory actually work when you try to apply it to the real world? Well, it turns out that Einstein and Kaluza and many others worked on trying to refine this framework and apply it to the physics of the universe as was understood at the time, and in detail, it didn't work. In detail, for instance, they couldn't get the mass of the electron to work out correctly in this theory. So many people worked on it, but by the 40s, certainly by the 50s, this strange but very compelling idea of how to unify the laws of physics had gone away. Until something wonderful happened in our age. In our era, a new approach to unify the laws of physics is being pursued by physicists such as myself, many others around the world. It's called superstring theory, as you were indicating. And the wonderful thing is that superstring theory has nothing to do at first sight with this idea of extra dimensions. But when we study superstring theory, we find that it resurrects the idea in a sparkling new form. So let me just tell you how that goes. Superstring theory, what is it? Well, it's a theory that tries to answer the question, what are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us. The idea is like this. So imagine we look at a familiar object, just a candle and a holder, and imagine that we want to figure out what it is made of. So we go on a journey deep inside the object and examine the constituents. So deep inside, we all know you go sufficiently far down, you have atoms. We also all know that atoms are not the end of the story. They have little electrons that swarm around a central nucleus with neutrons and protons. Even the neutrons and protons have smaller particles inside of them, known as quarks. That is where conventional ideas stop. Here is the new idea of string theory. Deep inside any of these particles, there is something else. The something else is this dancing filament of energy. It looks like a vibrating string. That's where the idea of string theory comes from. And just like the vibrating strings that you just saw in a cello can vibrate in different patterns, these can also vibrate in different patterns. They don't produce different musical notes. Rather, they produce the different particles making up the world around us. So if these ideas are correct, this is what the ultramicroscopic landscape of the universe looks like. It's built up of a huge number of these little tiny filaments of vibrating energy, vibrating in different frequencies. The different frequencies produce the different particles. The different particles are responsible for all the richness in the world around us. And there you see unification, because matter particles, electrons and quarks, radiation particles, photons, gravitons, are all built up from one entity. So matter and the forces of nature all are put together under the rubric of vibrating strings, and that's what we mean by a unified theory. Now here is the catch. When you study the mathematics of string theory, you find that it doesn't work in a universe that just has 3 dimensions of space. It doesn't work in a universe with 4 dimensions of space, nor 5, nor 6. Finally, you can study the equations and show that it works only in a universe that has 10 dimensions of space and 1 dimension of time. It leads us right back to this idea of Kaluza and Klein that our world, when appropriately described, has more dimensions than the ones that we see. Now, you might think about that and say, well, okay, if you have extra dimensions and they're really tightly curled up, yeah, perhaps we won't see them if they're small enough, but if there's a little tiny civilization of green people walking around down there, you make them small enough and we won't see them either. That is true. One of the other predictions of string theory. No, that's not one of the other predictions of string theory. But it raises the question, are we just trying to hide away these extra dimensions, or do they tell us something about the world? And the remaining time, I'd like to tell you 2 features of them. First is, many of us believe that these extra dimensions hold the answer to what perhaps is the deepest question in theoretical physics, theoretical science. And that question is this. When we look around the world, as scientists have done for the last 100 years, there appear to be about 20 numbers that really describe our universe. These are numbers like the mass of the particles, like electrons and quarks, the strength of gravity, the strength of the electromagnetic force, a list of about 20 numbers that have been measured with incredible precision, but nobody has an explanation for why the numbers have the particular values that they do. Now, does string theory often answer? Not yet. But we believe the answer for why those numbers have the values they do may rely on the form of the extra dimensions. And the wonderful thing is, if those numbers had any other values than the known ones, the universe as we know it wouldn't exist. This is a deep question. Why are those numbers so finely tuned to allow stars to shine and planets to form when we recognize that if you fiddle with those numbers, if I had 20 dials up here and I let you come up and fiddle with those numbers, almost any fiddling makes the universe disappear. So can we explain those 20 numbers? And string theory suggests that those 20 numbers have to do with the extra dimensions. Let me show you how. So when we talk about the extra dimensions in string theory, it's not one extra dimension, as in the older ideas of Kaluza and Klein. This is what string theory says about the extra dimensions. They have a very rich intertwined geometry. This is an example of something known as a Calabi-Yau shape. Name isn't all that important, but as you can see, the extra dimensions fold in on themselves and intertwine in a very interesting shape, interesting structure. And the idea is that if this is what the extra dimensions look like, then the microscopic landscape of our universe all around us would look like this on the tiniest of scales. When you swing your hand, you'd be moving around these extra dimensions over and over again, but they're so small that we wouldn't know it. So what is the physical implication, though, relevant to those 20 numbers? Consider this. If you look at the instrument, a French horn, notice that the vibrations of the air streams are affected by the shape of the instrument. Now, in string theory, all the numbers are reflections of the way strings can vibrate. So just as those air streams are affected by the twists and turns in the instrument, strings themselves will be affected by the vibrational patterns and the geometry within which they are moving. So let me bring some strings into the story. And if you watch these little fellas vibrating around, they'll be here in a second right there, notice that the way they vibrate is affected by the geometry of the extra dimensions. So if we knew exactly what the extra dimensions look like, we don't yet, but if we did, we should be able to calculate the allowed notes, the allowed vibrational patterns. And if we could calculate the allowed vibrational patterns, we should be able to calculate those 20 numbers. And if the answer that we get from our calculations agrees with the values of those numbers that have been determined through detailed and precise experimentation, this in many ways would be the first fundamental explanation for why the structure of the universe is the way it is. Now, the second issue that I want to finish up with is, how might we test for these extra dimensions more directly? Is this just an interesting mathematical structure that might be able to explain some previously unexplained features of the world, or can we actually test for these extra dimensions? And we think, this is, I think, very exciting, that in the next 5 years or so, we may be able to test for the existence of these extra dimensions. Here's how it goes. In CERN, Geneva, Switzerland, a machine is being built called the Large Hadron Collider. It's a machine that will send particles around a tunnel, opposite directions, near the speed of light. Every so often, those particles will be aimed at each other, so there's a head-on collision. The hope is that if the collision has enough energy, it may eject some of the debris from the collision from our dimensions, forcing it to enter into the other dimensions. How would we know it? Well, we'll measure the amount of energy after the collision, compare it to the amount of energy before, and if there's less energy after the collision than before, this will be evidence that the energy has drifted away, and if it drifts away in the right pattern that we can calculate, this will be evidence that the extra dimensions are there. Let me show you that idea visually. So imagine we have a certain kind of particle. It's called a graviton. That's the kind of debris we expect to be ejected out if the extra dimensions are real. But here's how the experiment will go. You take these particles, you slam them together, and if we are right, some of the energy of that collision will go into debris that flies off into these extra dimensions. So this is the kind of experiment that we'll be looking at in the next 5, 7 to 10 years or so. And if this experiment bears fruit, if we see that kind of particle ejected by noticing that there's less energy in our dimensions than when we began, this will show that the extra dimensions are real. And to me, this is a really remarkable story and a remarkable opportunity. Going back to Newton, with absolute space, didn't provide anything but an arena, a stage in which the events of the universe take place. Einstein comes along and says, well, space and time can warp and curve. That's what gravity is. And now, string theory comes along and says, yes, gravity, quantum mechanics, electromagnetism, all together in one package, but only if the universe has more dimensions than the ones that we see. And this is an experiment that may test for them in our lifetime. Amazing possibility. Thank you very much.
That's absolutely fantastic.